Hi everyone, this is Maths for Uni. This is question 1J from MAT 2019. The question says, an equilateral triangle has centre O and side length 1. A straight line through O intersects the triangle at two distinct points P and Q. The minimum possible length of PQ is A, a third, B, a half, C, root 3 over 3, D, 2/3, or E, root 3 over 2. So to start with this question, it's best to draw out some diagrams to see what's going on. We have our equilateral triangle like this, and we have our centre of our equilateral triangle at O. This is where the lines that go through the vertices of the triangle and bisect the opposite sides intersect one another. This equilateral triangle has a side length of 1, which, because I've drawn these lines down, I might as well have a 1/2 in all of these places here like this to have a side length of 1 on each side, and each of these angles will be 30 degrees because, again, we have bisected them. Then we have a straight line that comes in, goes through O, and intersects the triangle at two distinct points P and Q. I won't draw on such a line because our diagram is already looking quite messy, but I will use this tool here to kind of sketch out some possible lines of this form. It has to go through O, and so some of these lines as examples have already been drawn. These lines here, here, and here are 3 possible examples, but we could also have any straight line that goes through this centre O and intersects the triangle at 2 distinct points. Because of symmetry, we can restrict to considering only one of these 6 sectors of the triangle that we have formed by these bisecting lines. Again, this is because of symmetry, and we can reflect the triangle in order to see that we only need to consider, say, this sector here. We notice by eye that the lines here and here are maximal for lengths that intersect this triangle and go through O, i.e. these are the maximum possible lengths that we can get by doing this process. We're looking in this question for the minimum possible length, and so if we have maxima here and here, then there would need to be some minima in between these two lines, i.e. somewhere like the line which is the following. Again, the line is only actually between here and here. I just extended it for no particular reason at all. But because of symmetry again, we can notice that this line needs to be exactly halfway between these lines here and here. Again, because essentially a line that would be here is the same as a line that would be here because of symmetry. Therefore, the line that gives us the minimum possible length, at least in this sector here, must be the line that looks like this. And again, I'll just redraw that slightly to make it look a bit better. And the nice thing about this line is that because it's halfway in between, the angle which is here needs to be also 30 degrees. This information will help us to calculate the minimum possible length. If I draw on P here and Q here, then we need to find the length that's between here and here. If we calculate the length O to Q first and then double it again by symmetry, then we can get our answer for the length of PQ. This can be done by drawing out this triangle that appears here, but with more information on a separate diagram. Again, quite nicely because of our symmetry and our angles. This angle here is 30 degrees, and so is this angle here. And so we have an perfectly isosceles triangle. O appears here in this diagram, and Q appears here. And the corner of the triangle, let's say A, appears here, and on this diagram appears here. We're interested in finding this length O to Q here, and then doubling it to give us the length of PQ. But we do not have any lengths on this diagram to begin with. It would be helpful if we could identify, say, the length O to A using properties of this equilateral triangle, i.e. that O is the centre. And if we do this on yet another diagram, let's say the diagram that includes, let's have a look, this triangle here. So if I draw that out, let's call that point there that bisects that line B. Then we can draw out the triangle that looks like this. This is a right angled triangle due to the bisection, i.e. there's a right angle here and here. Then we have B here, O here, and A here. Because this overall equilateral triangle has a side length of 1, the length BA is 1/2. And we also have that the angle here is 30 degrees. We're looking for the length O to A so that we can use it in our above diagram, and by some right-angled triangle trigonometry, we can work out that if we call this, say, x, then x is such that, let's have a look, 1/2 is equal to x cos 30, because this length or side here is the adjacent to this angle 30 degrees here, and x is the hypotenuse. Then by dividing, we get that x is equal to 1/2 cos 30, and cos 30 is root 3/2, and so we have 1/2 times root 3/2 in the denominator, which is 1/3. Then we can use this length O to A, which we called x, in the diagram above. Namely, we have 1/3 for this length here. In particular, this length here to here is 1/2√3 by halving. Then we can call O to Q y, and then solve for y using yet another right-angled triangle with the right angle here. Y will be such that 1/2√3 equals y cos 30. Again, cos 30 is root 3/2, so we get 1/2√3 equals y root 3/2, and then we solve to find that y equals 1/√3 all squared, which is 1/3. Finally, recall that y is the length O to Q. We're interested in the length P to Q, and so therefore the length P to Q is doubling this 1/3, which gives us 2/3. Hence, our final answer is D. This may have seemed like a strange explanation to the solution for this question. That's because our original setup used a lot of symmetry in order to identify the correct line P to Q to consider. But after we had used that symmetry, it was quite easy to use right-angled triangle trigonometry in order to find the length O to Q and then double to get the length P to Q. If you've enjoyed this video, then please consider liking and subscribing, as well as checking out our full Udemy course, of which the link is in the description. Thanks for watching, and goodbye for now.